Yes, but
Sorry.
It's in August, so all the days are similar.
Yeah, but especially this one. Just for information, this one is a bank holiday in France. So we are very, very fortunate to have Paco with us.
Thanks a lot, Paco.
Yeah.
Are we waiting for? Is it? No one. Just,
no, only Lynn to discuss a little bit the construction of the surrogates.
Lynn, you want to take a go ahead?
Yes. I analyze the model. Lynn is with you or is connected?
Yeah, Lynn is connected, and I think Lynn is going to share his slides and maybe his video.
Okay. Perfect.
Yes, great.
Okay,
hello, Lynn.
Hi, Paco. So maybe I explain a bit for the slides we sent to Paco.
Yeah.
Perfect. Just for your information, Paco, we just had like an hour-long discussion between Lynn and myself on all of this and how we hope that this will help us to have a better understanding on hybrid AI. So really like diving into those surrogate models that you've been working on.
Perfect.
And trying to connect it to the bigger picture. And so right now we're looking at more a component level, and then we'll be trying to get knowledge to move more on the system of systems, like we discussed earlier.
Exactly.
So first of all, thank you, Paco. Thank you so much for having looking my surrogate model. It's extremely complicated differential equations, but I think it's very good and very appreciated. You find out nonlinearities inside. So first of all, thank you very much. I think from the meeting we have last time, you and Blake said we can start from a very simple model, so that we can try if we can use if we can successfully use the hybrid AI method. So now I discussed with Edward, and we think we can start from model 0. Yeah, I think this is you are very familiar with these equations. I presented to you last time. We have some we have the objective function, and we have some constraints, and all of these parameters I have provided in I have found out all the necessary parameters in this optimization model. And one more thing is that last week we had a meeting with Blaise. Blaise and Arwin, who is the associate professor from NTU, they are interested in developing they are interested in using reinforced learning to solve the optimization problem.
Exactly.
Yeah, they want to use RL to find out long scale decision variable first, and after fixing this long scale decision variable, they can simplify the model into linear programming problem, which is easy to track it, which is easy to solve it. So based on their idea, based on their concepts, I realized that in our power system context, we have already some similar modeling methods for the optimization problem. That is the kind of things called two-stage optimization problem. So for now, there are many two streams of two-stage optimization things. The first is two-stage stochastic optimization, and second one is two-stage robust optimization. So maybe I from myself from EDF side, I will provide. I will do this kind of two-stage optimization first to provide a benchmark for Blaze team. And they will use the reinforced learning to solve the optimization problem. Then we compare the results from our side and the Blaze side.
Perfect.
This is what I think for now, and discuss about when we speaking of hybrid AI concepts, right? So for this optimization model in these slides, we don't have the concept of hybrid AI. So I think your previous slides, based on your previous slides, your previous presentation.
Maybe before moving to model 1. Yeah, maybe we can take a pause here. So what Lynn tried to do is really to have a very simple model, the simplest one as we can. Actually, we could make it even more simpler if you want to remove the ESS, but we would get it would start to have not so much interesting meaning. So this is the most basic version that we can imagine of this problem.
Perfect.
Do you think is it matching your?
I think the idea is to solve this optimization problem by using, as Blaise commented, reinforced learning. The only problem in reinforced learning is not hybrid in the sense that we are only trying to minimize this cost function by using reinforced learning, but there is not a lot of physics. The physics is in the surrogate, but we need to discuss about what is the connection between the surrogate and the optimization model that I think is in the next slide of Lynn. But from my side, this is the minimum model that we need to solve. And I think if it has sense for you, the idea of trying to use reinforced learning and compare with the two-stage stochastic optimization or the two-stage robust optimization that you are using, I think it's a very nice start for the research.
Is it our understanding? Do we have a two-stage optimization?
Yes, for this we can the model in this box is the typical very simple model, so as we call it model 0. And I do the reading in these 2 days, and I know how to formulate the overall model into a two-stage model. So the thing is that just look at this objective function.
Exactly.
Yeah, this is a typical two-stage stochastic optimization problem. So the thing is that for first stage, this is the first stage decision variable. PU it is the power exchanging with a utility grid, and this is the second stage decision variable, which means for real-time operation, when you see the variation of PV, you can redo the optimization model. So it's kind of things like incorporate the real-time optimization model into the day-ahead optimization model. So that's so-called two-stage things.
Perfect.
So I think for Blaze team, if they want to use reinforced learning to solve the problem, is for the beginning step. The first thing is to use RL to find out what is the best PU. What's the best exchange with the utility grid?
Exactly.
Am I clear?
I think so. Yeah. Okay, good. So we have our model 0 that will be the
exactly.
Good.
Yeah.
Then so we can hope that we'll be able to solve it, get the same results, and have our baseline to go further.
Yeah.
Exactly.
That's what we call model 1.
Exactly.
Yeah. So the next one is to slightly touch the concept of hybrid AI.
Exactly.
Yeah. So to my understand, the hybrid AI means the hybridization or combination of original physical things plus Paco said data-driven or model-driven based on neural network or whatever. So here because it's not possible to directly incorporate these nonlinear differential equations directly into this optimization constraint set. So one possible way is to use a neural network as a surrogate model, and because we know that a neural network is a convex optimization problem, so it's a convex function. So we know that it's possible to substitute this surrogate neural network model into this constraint set, and then we can consider we can resolve this optimization problem by because for now we have already the surrogate model here, so we can care more about the system dynamics, and we can care more about the system performances in small time scales.
Yeah, I have two questions in this point. Having something that is convex, today it's very easy to create a neural network that is convex. So ensuring convexity, this is good. My question is with respect to the nonlinear dynamical system that I'm working in. I'm working in this part that is in the right. So my question is, this is a dynamical system. When you are speaking about a surrogate, this means you are trying to relate some inputs with some outputs. I understood that the inputs are the currents. Maybe it's in the next slide. I don't remember the name. Can you move to the next slide? Yes, this one, the previous one, the previous one.
This one.
This one. Yes. My question is here, the surrogate that you are looking for is the one that appears on the top on the left. You are trying to obtain omega, that is the frequency, depending on the inputs. And for me, the inputs are the intensity OD and the intensity OQ. I'm right?
The input of this model will be these two variables.
Exactly. And the other are the state that is evolving in time, that are different currents, different voltage, the frequency, etc. So the inputs is these two currents that you put in red. I fully agree with you. And the output that you are looking in your surrogate is omega, because it's the one that is moving to the optimization problem.
Yes.
I'm right?
Is frequency involved in?
Yes, in the previous slide, this omega appears in the constraint in the model 1 on the bottom. The frequency omega should be in this interval, that we are defining in this slide, in between 49 and 51, right?
Yes. The inputs of the model is the power. So these two values is related to power of the.
Exactly, because is the current multiplied by a voltage, but the voltage is changing in time, because when you are asking more current, obviously we assume that the current is the control, and obviously this current that you are asking to the system is modifying the voltage. For this reason, the voltage is in the time derivative, and these are something that you are asking to the system. This is the real input. that is related, obviously, with the power, the loading of the system. Lynn, can you hear me?
I can hear you, Paco.
Yes. Oh, I lost you for a few seconds. My question to Lynn was that these currents are something that we enforce in the model, and the output is the omega, that is the one that is moving to the optimization problem, right?
The input of the model is the current, the output is the omega.
Exactly. And you would like, if you come back to the previous slide, this means that this should be correct for any tau in 0 delta t. This means that when we are optimizing in t, we need to have an idea about the next delta t. For me, the question is, this is a transient problem. It's a dynamical system.
This is a transient problem.
So when you are optimizing a time t, you need, if I understood correctly, in this square in green, when we are optimizing a time t, I need to certify that the omega is always in this interval for any time t, that is the time at which I'm making the optimization, plus tau. And tau is in the interval 0 delta t. And my question is, this delta t, what is the value of this delta t?
Okay.
Is 1 second, is 1 hour, is... Yes, exactly.
Okay. I think I didn't explain this this model, this point very clearly. What I mean is that for this kind of model, the decision variable, like for example, we have 24-hour decision variable, and for example, the power exchange with utility grid is like this one,
Mm-hmm.
For example. And this is first hour, and this is second hour, and this is a third hour, right?
Mm-hmm.
This result is given by the model. Is given by the optimization model, and we take care. We want to see during. If you don't consider this differential equation, maybe you have a set of decision variable like this. I just draw it, and if you consider a differential equation here, that means you reduce the feasible state. You add some constraint asset to this optimization problem. So the result will be smoother. For example,
perfect.
Yeah, if we consider this constraint state, maybe the result will be smoother, like this one.
Okay.
So this kind of relatively smoothly change the power exchange with the utility grid will help to stabilize or maintain the system frequency in a more desirable range. And this is
I understand, Lynn. My question is, you are at time t because you are performing the optimization at time t. When you are trying to enforce this constraint in t plus delta t, my question is, if delta t is 44 hours, is 1 day, the delta question is
1 hour.
Is 1 hour, okay. And what is perfect? But this is the future. because I understand that this is in omega t plus delta, t plus tau. So my question is, as we are in the future, what is the value of the currents that you are introducing in your dynamical system? Because you are evaluating this, if I understood correctly, you are optimizing all the variables are at t, time t, and this constraint that is coming from the differential equations are in t plus tau. And tau is something in the future, in the next hour. And my question is, if you are evaluating something in the next hour, what is the value of the currents that we are introducing in the nonlinear dynamic system in the next hour in order to take a decision now? Because your optimization problem is in time t, and this constraint is in the future, is in the next hour. So my question, this is my question.
Oh, okay, sure. For example, we have let's say we stand here. Let's say we starting from here. This is time t, right?
Perfect.
So once for example in the time instant of t, we have a decision variable, right? So if we don't have this surrogate model, yeah, we just have this very simple conventional model. This value will this value will not see how the frequency behave from this time t.
Perfect.
So the result is that so that's why I put a t omega t plus tau. That means if we can input the decision variable here into this neural network or into this differential equation, there will be a kind of omega like this one, like this one.
Yeah, I understand. But what is the current I0D and I0Q that you are putting when you are in the future?
Okay.
Because now you know everything until t, and now you are projecting in the future. And my question is, in the dynamic system, what is the input that you are introducing in the future, in the next delta t? This is my question.
Because in the future, the value of input will be maintained at time t, at a value of time t.
Okay, perfect. So this means in the next delta t, I assume that the input is the same
constant
that I have now.
Yeah.
Perfect.
Right.
Perfect.
Right.
Perfect.
Yeah.
And another question for you, Lynn. Delta t is 1 hour. When you are solving this nonlinear dynamic system by using MATLAB or finite difference or the method that you want, what is the delta t? Is different. It's not the delta t of 1 hour. It's in your dynamical system. Maybe you can move to the next slide. Lynn, move in this one. What is the delta t that you are using in order to integrate this dynamical system? Is 1 second, 1 minute?
I think it depends on how it depends on what it depends on the time resolution we are interested in. Of course, in my MATLAB simulation, the time resolution, this is frequency, for example, and this is time t.
Perfect.
For example, in my resolution, the simulation resolution is 1e minus 5 second. Sorry,
I repeat. This means 0.0001 seconds, right?
Yeah, right.
Very, very small. For this reason,
Yeah. So
is even if the system is very simple, simulate one hour, it takes millions of time step.
Yes, I know. What we are interested here is to know the for example, in power system, we know the frequency is 50 hertz, right?
Okay.
So we are interested in the maximum frequency deviation from the nominal frequency 50 hertz. So the output of this neural network will be a value like delta f.
Mm-hmm.
So we can use although we are talking about the dynamic system from dynamic behaviors from 0 to delta t, but if we are only interested in the maximum frequency deviation, so it's very simple. The output of this the input of this neural network will be the current or power of the converter, and the output will be only a scalar like delta f. So we want to limit this delta f within like 0.0 hertz or something.
Perfect. So this is the reason that the integration of the dynamical system is not compatible with the optimization problem.
Yeah.
Okay, and this means you are interested, obviously, in creating this surrogate that is giving you the frequency everywhere. This means at any time in between one time and the next hour. Yeah. With a very fine resolution, right?
The neural network will be the surrogate model that will give
exactly.
you what will be the frequency range between your two time steps.
Yeah, between my two time steps.
Between 0 and 0 plus delta t.
Exactly.
Oh yeah, right. Like for the future, like if we want to consider more practical case studies or more practical demonstrator, it's also possible to use this kind of surrogate model to I'm not very clear in my mind now. We can use this model to provide a frequency reserve frequency supporting or frequency regulation service. Provide this kind of service to power system and make money and then earn money from utility system. But this is not very clear now, and I think we may do it in the future studies.
Perfect. Yeah. I will. It's very clear for me, Lynn. Is much more clear. Obviously, the surrogate will be a little bit more complex. I will explain why. Because you cannot obtain a surrogate between the currents and omega. It does not exist. You are in a dynamic system. So this means that you can obtain a surrogate between the currents in the past, and omega. This is because you have a dynamic system, and you cannot create an instantaneous model that relates the frequency omega and the currents as an input. Because as you are in a dynamical system, you agree with me that everything depends not only in the present values, but also in the previous ones, because when you have a dynamic system, you need an initial condition. So this means that we should give, because everything depends. If you are moving to the next slide, Lynn, move to the next. You have plenty of dots. You have I dot, V dot, V dot, omega dot, phi dot, V dot, U dot, etc. So there are many dots. And dots means this is a difference in time. So this means that in order to evaluate the frequency with respect to the current now, I need a series of initial conditions for all the variables that are involved in the dynamic system. So this means that I cannot create a surrogate that directly relates current and omega. I need current, and the current in the previous time steps with respect to omega. There is a kind of history, and this history is very important in the creation of the surrogate because it's the one that is taking in charge all the dots that appears in the left-hand member of all the equations in your dynamic system. You understood me?
Yeah, I understand.
But I'm creating that. There is no problem. I will elaborate a little bit the model, and I will come back to you for the end of the week. Now it's very clear.
Yes. And for now, we can consider a very simple case. We don't need to do any prediction in this constraint set. We just need to know what is the maximum frequency deviation. Perfect. Instead of knowing the entire frequency behavior, frequency dynamics within zero and delta t. So this is over complicated. We can start from a very simple neural network. Yeah.
We are trying different alternatives. But maybe we could create also all the history of omega in the interval. I think this is not a limitation.
Oh, okay.
Okay, it's very clear, Lynn.
Yeah.
I think I need a couple of days in order to advance with this, and I will share a report for the end of the week about the creation of the surrogates. As soon as we agree, I could ask my team to start to produce results. The idea is to having something for the end of August.
Yeah, the thing is that I have already done the simulation in MATLAB, and for me, I can provide any training data that you need to generate this model. Yeah. So maybe if we can. It would be great if you can introduce me one of the researchers in your team. We can have a detailed discussion. I can have detailed discussion with him or her to see how we can derive this model, because I have already done something here.
This is perfect.
And I have better understand of this dynamic model.
It's very clear, Lynn. I will check everything in order to have different alternatives. And next time in our meeting at the end of this week or beginning of next week, I will invite some people in my team in order to start to explore different alternatives to create the surrogate. Maybe we are not using only a neural network. Maybe there are different opportunities, and the idea is to create different surrogates depending on the technology that we are using. So I will introduce, obviously, I will inform you, and I will introduce the members of my team that will work in the surrogate.
Yeah, sure. Thank you.
I think since it's the beginning now, we need to fine tune together on the model 0, model 1, etc. And have I think we need to have regular meetings.
I think we can finish saying. Remember that I just talked about the first stage thing or two stage thing. So I think it's better to incorporate this surrogate model and to further investigate how the RL can find out the first stage solution for this hybrid AI model. So yeah. So the result, the output of this work will be the input of Blaze team for next step.
Yeah, exactly. We are creating the surrogate, and this will be one input in the optimization of Model 1. This is perfect for me. And I will be in Singapore for 1 month, from 15 September to 15 October, with my team. The members of my team are coming with me. So this will be also an opportunity to discuss and to work in the surrogates together.
That's the question I had for you, Paco. When you're referring to your team, it's like people involved in Descartes officially, or is someone like from your lab? I don't know.
Yes, it's all the researchers of my lab, but they are also part of Descartes. So all the people working with you are people in my lab. They are not paid. They are not paid by Descartes, but they are people that are in Descartes.
Okay, yeah.
How can we move forward there? So I understand there is one stream of work which is Model 0 to make sure that we get the same result on reinforcement learning approach versus like classic tools. So that should be maybe let's not call it work package, because work package is already a word that is used elsewhere in Descartes, but it could be a streamline. So we need to evolve there, and the goal of it is quite easy. It's to make sure that we get the same results with the RL approach and the other one. So that's the first line of work. Line 2 is to work on the surrogate model itself. To make sure that the neural network is able to replicate what you get on your MATLAB.
Exactly. And there are two teams, Blaise and Arvind, that are working in the reinforcement learning. This is Model 0, and myself and my team, we are working in the surrogate. That is one part of Model 1.
So who is working on Model 0? Sorry, I didn't get the name.
Blaise.
Okay.
And Arvind.
The co-directors of Descartes. So one on the French side and the other on the Singaporean one.
Exactly.
Arvind is at NTU for you, Edouard.
Good. Okay, so
Indian guy.
Good. Excellent. So, and then there will be extra step, which will be combining these two.
Exactly. So the idea is, at least for 15 October, it will be great proving that Model 0 works. This means with reinforcement learning, we are obtaining the same results that you obtain with your standard optimization technologies, and maybe faster, obviously. And the second is we can create a surrogate of the dynamical system in order to prepare Model 1. But obviously, if we can prove that by using MATLAB and by using the surrogate, we obtain the same results with respect to the surrogate, and that with respect to Model 0, by using reinforcement learning, we can obtain the same result that you obtain by using other technologies, this is an excellent starting point for the next.
Okay, so that should be the target for October 15th.
Right. Absolutely. This is the idea. Both. Yes.
Okay. How do you want to proceed, Paco? Do you want to work as two separate streams of work, one on Model 0 and one on the surrogate model?
Maybe I propose that there is a first meeting in which we can define the two work that we are developing in parallel, because it's not necessary to be involved in the reinforcement learning or people from reinforcement learning in the surrogates. So I would like organizing a meeting, maybe tomorrow, but tomorrow I have a problem in the slot that you define, because I have another meeting with NUS. But the idea is, in a first meeting, define the two works to be developed from now to the 15th September in the first month, and after we are trying to couple. And obviously, there are two different teams, one team working in the surrogate and one team working in the rainforest learning. And after, for the technical meetings concerning the rainforest learning or concerning the surrogates, there are two teams and two different meetings in order to be more efficient.
I think we need to organize weekly meetings
exactly,
for now,
exactly.
To make sure that we move on at good path, because October 15 will come very soon now, and we need to make sure that we align. So let's have, so I guess it will be even two meetings a week, one for each.
Yeah, exactly,
stream,
exactly,
right?
exactly.
So I think, Lynn, it'd be good if you can take the lead on that, organizing these meetings. I think from now you can send invitations to every week, to everyone for every week. So 2 invitations. There will be one stream of work and one other stream of work, maybe starting from next week. And so tomorrow we have the meeting with
Blaise and Alvin.
Machine learning team, yeah.
Perfect.
Where did you want maybe us, Paco, to be explaining that tomorrow? I know you won't be able to be there. Did you want us to reschedule it so that we find a place?
Yes, if you can reschedule, maybe 1 hour before or maybe 1 hour after. My only constraint is from I think it's from 9 to 10. I'm check. So tomorrow, except from 10 to 11, that I have another meeting, I'm fully free. So you can reschedule the meeting. I will explain to the teams that we are working in 2 working teams, one working in the optimization, another in the surrogates, and I'm taking the lead of the surrogates, and probably Blaise or Benoit or Arvind, or I don't know, take the lead of the optimization problem.
We might have constraints tomorrow because everyone is not available on Descartes' side. What about your other availabilities, Paco, this week? Do you have any?
Wednesday, I'm fully free.
Fully free on Wednesday.
And Thursday, I'm fully free.
But Friday, not.
And Friday, normally I'm fully free.
Okay. So you have the global picture.
Exactly.
Yeah.
Great. Good.
Perfect.
Are we done?
We continue working on that, and we meet, I don't know, tomorrow or during the week, and we organize the work with all the other people. Okay?
Right.
Perfect.
Do you have any other things to explore, Lynn?
No, it's very clear. It's very clear.
Okay, great. So let's move on this way. Lynn will reschedule the meeting of tomorrow, and Lynn will send
perfect
2 weekly invitations.
Perfect.
Yeah.
2 streams.
Yeah.